Hey, good morning, Excel Geo. What we're going to do is go over the area of the sector worksheet that we had for an assignment yesterday. Now, you did the Desmos activity, and during the Desmos activity, you should have been able to derive the area of the sector formula. Now, an area of a sector, the sector is formed by two radii and their intercepted arc. So, when you look for a sector, the vertex of your angle that is formed by the two radii is always the center of the circle. You have two sides that are the radii and an intercepted arc here. And in this case, your radii dr, your other radius ar, and your intercepted arc is dA. So to find the area of that sector, you're going to take the measurement of that central angle, put it over 360 degrees, which is the total number of degrees within a circle, and multiply it by the area of the circle formula, which is pi r squared. So you're taking a portion of that circle, a fraction of that circle. So if I take a look at this problem, I would say 45 degrees over 360 times pi r squared. So which in this case is my radius is 3 squared. Now I can reduce that 45 and 360. Now if I think about that, 45 goes into 360 8 times. So this is the same as 1/8 pi, 3 squared is 9. So if I asked for the answer in terms of pi, I would say 9 pi over 8. That's what I mean when I say in terms of pi. Since it's area, it's going to be centimeters squared. If you had to find the exact value, you would just put that into your calculator, 9 pi, and if you had to find an approximation, and it's not exact, this is actually an exact value because I did not round it. But if you were asked to find an approximation, a decimal form, you'd put 9 pi divided by 8, and you would get this to be approximately 3.534. And again, centimeters squared because we're talking about area. So those would be my two answers, or two possible answers. This answer in terms of pi, and that's in decimal form. And you'll notice I like to round everything to 3 decimal places when I put it in decimal form. All right, guys? So now let's look at our next problem. Right here, I shaded the regions. This is an 80-degree angle. So again, you're doing, if I'm finding the area of that sector, you have 80 over 360 times pi times 4 squared. 4 is my radius. Now, if I want to think of 80 and 360, I'm going to simplify that fraction. And it's going to be 2/9 because 40 goes into both of them. 40 goes into 82 times, 360 9 times pi times 16, because 4 squared is 16. So if I wanted to rewrite this in terms of pi, it would be 32 pi over 9 centimeters squared. If I wanted to find an approximation, a decimal answer there, I would take the 32 pi divided by 9, and it would be approximately 11.170 centimeters squared. All right, and it's important to put the centimeters squared because it is area, because we're trying to see how many centimeter squares can fit within our area of our sector. Now here we have meters, so I'm just going to be using meter squares in number 2, but our angle is 62. So if I look at this one, I'm doing 62 over 360, pi, r being 2.5 squared. Now if I look at that 62 divided by 360, and I say what goes into both of them, it's 2. 2 goes into 62 31 times, into 360 180. All right, and then if I do 2.5 squared, what we're going to get is 6.25. So now if I multiply this out, I multiply 6.25 times 31 and divide it by 180. I'm getting it to be a 1.076 pi, which is also an approximation because I rounded that decimal because the fraction would have been 155 over 144, which is also a possibility. You can write 155 pi over 144. And that would be, again, meters squared. If I wanted to find an approximation, I can take that value, multiply it by the pi, and I would get this to be approximately 3.382 meters squared. All right, guys, so these would be my answers. All right, guys, let's flip it over. All right, let's take a look at 3 and 4, which is what you had last night. All right, again, I'm going to color these in. We're going to use, because I assume everyone used the 20 and then the 156. We're going to use those. So if I take a look at 3, I'm going to say if I take a look at the problem, I'm doing, again, 20, the central angle, over 360 times pi times 3 squared. Now, if I simplify this, 20 goes into 360, 1 over 18 times pi times 9, because 3 squared is 9. So if I take a look at this now, what we have is 1/18, 9 over 18, which would be 1/2, so I get pi over 2, and that would be meters squared if I simplify that. Again, you can find an approximation by plugging that into the calculator. This is approximately 1.571 meters squared. So this would be your answer in terms of pi, and that would be your approximation. All right, and number 4, 156 over 360 times pi r. In this case, they gave me the diameter, so I'm going to divide that by 2, so I'm going to get 15 squared. So if I take a look at this, and I want to know what I'm going to do is I'm going to take a look and I'm going to try to simplify that fraction. And if I take a look at that, 18 is actually going to go into both of them. 18, I'm sorry, not 18, I'm sorry, guys. So if I take a look at that, what's going to go into both of them is 12. So I have 156 divided by 12 is 13, right? And then I know 360 divided by 12 is 30, right? And 15 squared would be 225. So if I take a look at that, I'm going to simplify that. 13 times 225, and if you divide that by 30 and simplify that fraction, you would get 195 over 2. So you have 195 pi over 2, and that would be meters squared. Now again, we can approximate that by actually finding the decimal value, multiplying by pi, and that is approximately 306.305 meters squared. All right, guys? So that should be what you had from yesterday. All right. Now what we're going to do today is just go over a couple other problems where we're going to be utilizing area formulas that you should know from previous years. So let's take a look at this. Suppose a baseball field is shaped like a quarter circle with a radius of 350 feet, as shown below. What is the area of the outfield? So here they're asking the area of this shaded region. Now let's think about that. This is 1/4 of a circle. If I'm looking for the area of 1/4 of a circle, I would take 1/4 of my circle's area, which is pi r squared. Now, if I'm looking for the shaded region, this now 1/4 pi r squared would give me the region of this whole entire quarter of that circle. But I would have to remove the infield. So if I take a look, I would have to remove the area of the infield. The infield is a square. So that would be minus the area of the square formula would be sides squared. So that would be the area of my shaded region. If I know it's 1/4 the circle. So here I can say 1/4 pi, my radius is 350 squared, minus side squared. Well, the sides are 90, minus 90 squared. And you can, guys, input this as an example that you can input right into the calculator and just tell me what the approximate answer would be. All right, guys, and if you input in the calculator, you should get this to be approximately 88,111.275, and we're looking feet squared. That should be our answer. All right, guys? So you're taking the area of the whole quarter of a circle, and subtracting the area of the infield. Now that same process applies to the rest of them. So now let's look at 6. In 6, the outside is a square, and the inside is a CD. You guys probably don't have CDs anymore, but we had CDs when I was younger. So a CD with a diameter of 12 centimeters is placed into a square case, which measures 13 centimeters along a side. How much space is around the CD? So again, we're looking at the shaded region. The difference here, if I'm looking at the area of the shaded region here, again, you're looking outside minus inside. In this case, the outside is the area of the square, minus, in this case, is just the area of the circle, which is pi r squared. So if I look at this, I'm getting 13 squared minus pi. Our radius, remember, they gave me my diameter is 12, is 6, so 6 squared. So again, input that into our calculator. And if you input that into your calculator, you can get me an estimation. 13 squared minus pi times 6 squared, which is 36. So this will be approximately 55.903 centimeters squared. And that would be the area between the CD and its case. Now down here it gets a little different. So we have to actually think a little on this one because we want the shaded region. And we have this square. Now this square was within our circle, but it's within not just one circle, it's kind of overlapping 4 circles. So we want to actually take a look at what we know. Now, if we do know all 4 of these circles have the same exact area, and the reason we know that is because they have the same radius. If 4 circles have the same radius, then each circle has the same area. Now, the whole thing is we have to determine how much of each circle is missing. Now, if this is a square, and you can see right here, there's this right angle. If this is a square, that means this is a 90-degree angle. So if I was to finish this circle there, the sector that is missing from that circle would have a 90-degree central angle. So that means in this circle, I'm taking out 90 degrees, I have 270 degrees remaining of my circle, because 360 minus 90 is 270. So one circle's area would be 270 over 360 times pi r squared. That would be the area of one of my shaded regions. Now, if I found the area of one of my shaded regions, and all 4 shaded regions are the same exact measurement, what I can do is then multiply this by 4. So I could put my radius in as 3. And I'm going to multiply everything by 4 because I have 4 shaded regions that are the same exact size. Now, if we think of this, 270 over 360 is actually 3/4 of my circle. Because if I took away 90, 90 is 1/4 of that 360. So it's 3/4 times pi times 9 times 4. Now, if you look at these 2 4s can cancel out using our basic math skills. Then I have 3 times 9, I have 27 pi. And this will be meters squared because it's area. And if I wanted to find an approximation, I would just multiply by pi. So I have 84.823 meters squared. Now this answer here is in terms of pi. And that's actually an exact measurement because I didn't round anything. And here is an approximation because I put it in decimal form and I rounded. All right. Now in part B here, again, we're doing outside minus inside. And we look at this circle here. And I have a rectangle inside a circle, and I'm looking to find the shaded region. So I really need to take the area of the circle and subtract the area of my rectangle. Now, what I wonder if anybody notices is that in your rectangle consists of 2 right triangles. And if I have a 5 and I have a 13 in that right triangle, what do I know the hypotenuse of that right triangle has to be? Well, it has to be 13, because that is one of my Pythagorean triples. Now, why is that hypotenuse so important? Well, that hypotenuse is also going to be the diameter of my circle. And the reason I know it's the diameter is because this is an inscribed angle, and it's 90 degrees, and that means its intercepted arc would have to be double its measurement, so this intercepted arc would have to be 180 degrees, because it has to be double the measurement of an inscribed angle. So if I look at this, I now know my diameter is 13, and therefore my radius will be 6.5. So if I look at the area of the circle, I'm saying pi times 6.5 squared minus the area of the rectangle. Well, the area of the rectangle would be length times width, which is 5 times 12. So if I put that into my calculator, I'm putting 6.5 squared times pi minus 5 times 12. We're going to get this to be approximately 72.732. This didn't have a unit measurement, so I'm going to put unit squared. So if you're finding area and there isn't like centimeters, inches, meters, yards, just put unit squared. To identify that you're finding area, we know we have to have some square unit there. All right. Good job. Last problem for today. So this one's a kind of an interesting problem, and I like it because it's going to bring back some trigs, some previous knowledge, and I love when we can pull previous knowledge into our mathematics. So if I look at circle P, Circle P is circumscribed around a hexagon, A, B, C, D, E, F. Now remember, when I say circumscribed, that means every single vertex of that hexagon is on the circle. The circle surrounds the hexagon, and every single vertex of the hexagon is on the circle. The perimeter of your hexagon is 108 inches. The radius of the circle is 18 inches. Now let's also emphasize, it said it was a regular hexagon. That's important too. That means that every single side is congruent. Every chord length here would have to be the same exact measurement. So then it said the radius of the circle is 18 inches. What is the percent of the circle that is not inside the regular hexagon? So they want me to find the percent of my circle that is out here. All right, so let's think about that. Percent of the circle that's out there. Well, let's first talk about area. Can we find the area of the circle and the area of the hexagon? And if we knew how much area that hexagon took up of the circle, we can find out what the remaining area is and then change it into a percent. Now you can change in percent by putting that area over the total area of the circle, and that would give you the percent of the circle that area covers. So let's start. The area of the circle is easy. You know the radius is 18. I can draw this here. That's a radius. That's 18. I know I can say the area of the circle is pi times 18 squared. So let's leave it in terms of pi for now. So that is 324 pi inches squared. So that was simple. But I need to figure out a strategy to find the area of this regular hexagon, because we have not learned that yet. But what we have learned is that a hexagon can break into, if that's 18, this is also 18, correct? Now let's think of this. The perimeter of the hexagon is 108. If that's the case, I can say, well, I'm going to take all of these sides. I have 6 sides. I'm going to take 108 and divide it by 6. That is also 18. Now, I'm going to tell you, I already knew that. And the reason I already knew that is because if you think of the interior angles of a hexagon, the interior angles of a hexagon add up to 140 degrees. Right? I'm sorry. The interior angles of a hexagon add up to 720 degrees. So the interior angles of the hexagon add up to 720. Now, if that's the case, there are 6 of them. 6 of them add up to 120. So that means this whole angle is 120. So if I split that angle in half, each angle would have to be 60 degrees. So if that was 60 and this was 60, this would have to be 60, and I would have an equal angular triangle, which would also have to be an equilateral triangle. So we know we have equilateral triangles here, and we know we have 6 of them. So if I take a look at one of those equilateral triangles, I have 18 here, 18 here, and 18 here. I'm going to drop a height. The reason I'm going to drop a height is because if you think about that, the area of a triangle is 1/2 base times height. Now, if I find the area of one of these triangles, I can multiply it by 6 to find the entire area of that hexagon. Now, there's some other knowledge. We know that this is 60. We know this is 60. So if we look at that, I hope all of you are saying in your head is like, wait a minute. If you drop that height, that altitude, this has to be a 30-degree angle, and we are working now with a 30, 60, 90 right triangle. So let's look at it. We have 18 is our hypotenuse. That matches up with 2n. Right here, half right there, that length. That is going to be 9, which is equivalent to n. And then our height should be equivalent to, if it's across from 60, n times root 3. So your height will be n times root 3. My height is n times root 3, n is 9. The height would be n root 3, which is also 9 root 3. So that means I now have my height and my base. My base is still 18 because the base of the whole thing is 18. So to find the area of one triangle, it's 1/2 times 18 times 9 root 3. And if we think about that, half of 18 is 9. 9 times 9, 81 root 3. And that's again in inches squared. But we need to subtract 4 of them. So if I wanted to find the area of the, in my case, the yellow region, because I shaded it yellow, it would be the area of that circle minus 6 times the area of the triangle, because there are 6 triangles in that hexagon. So let's take a look at that. So if I do 324 second pi minus 6 times 81 root 3, I should get this to be, the area of the yellow region is approximately 176.099. And that again is inches squared. But the question said, what is the percent? Well, to find percent, you take that area and put it over the total area. So to find my percent, my percent will be the area of the yellow region divided by the area of the entire circle, which is 324 pi. Now, I want to emphasize this is a common mistake when we put something in the calculator. Anytime you put a denominator in the calculator, even if it's a product of something, you must put it in parentheses. Otherwise, the calculator will first divide these two and then multiply by pi. So when you put that in the calculator, you need to have 176.099 divided by, in parentheses, 324 pi. And you should get 0.73. So I'm finding the percent, but this is actually the decimal form, right? So if the decimal, this is how much of the whole. And if I wanted to actually know the percent, I'd move my decimal 2 places. It would be 17.3% of the circle is in my yellow shaded region. All right, guys. So what you're going to do today is you have an assignment that's in your textbook. Okay, you can upload it. That's it for today. I'm also attaching a packet, which is an optional packet, reviewing area that you can look at over break, just if you are interested. If not, you can look at it when you get back from break, okay? So it's optional in the sense that it will be done after break and in addition to other stuff, or you can do it during break if you just want something to do. If you have any questions today, please come visit me during office hours, and I hope you guys have a great day and enjoy your break. Get away from your screen, take some walks, and relax. All right, guys? I hope to see you at my office hours. Have a good day.